let's continue. We'll talk about the thermal flame theory, and after that, I will, as promised, I will show you the difference between the diffusion and the Premix flame. So, the thermal flame theory.
Microphone?
Oh, sorry. So the thermal flame theory, what it does is it performs asymptotic analysis that ultimately leads to a relation for the burning velocity. And it's based on a few assumptions, and one, of course, here is a single one-step reaction. The reaction rate then can be expressed like this. And what's interesting here is you see that this is proportional here to fuel mass fraction, oxygen mass fraction, and has this exponential temperature dependence. That's what you would expect. But the original analysis here was actually done for, let's say, for just lean flames or just rich flames, where you then would say if you have a very lean flame, you would say oxygen will not a lot of the oxygen will be consumed. So oxygen stays almost constant, and then the reaction rate just depends on the fuel mass fraction and so on. Here we'll keep all these different contributions. So this, I should point this out, this was done here in 1938 by Zeldovich and Frank Kamenetsky. So, right, so I just mentioned this. You can do the analysis with rates that are first order with respect to fuel, but here we want to keep both of these. You see that the activation energy appears here. One thing I might have mentioned already or not, I don't remember, is that for one-step global reactions, the activation energy always is much higher than the activation energy of any elementary reaction that's involved. Why is that? That is because in reality, for multi-step chemical kinetics, real elementary kinetics, you have reaction rates that depend on temperature exponentially, and they have an activation energy. And that causes a nonlinearity. But in addition to this, you have different reactions competing with each other. And in the next lecture, actually, we'll see a very good example for that. And this competition between two rates, that leads to very abrupt shut-off of one reaction or enabling of another reaction at certain temperatures. And that leads to very strong nonlinearities. And these nonlinearities that come by competition of different reactions, that, of course, in a one-step reaction, they are not included, which is why the nonlinearity that you have in the combustion process in a one-step reaction, it needs to be expressed all just by the activation energy, which is why the activation energies for one-step global reactions are typically very high. Okay? And so here, the analysis also makes the assumption that the activation energy is very large, and that is justified for very often for one-step global reactions. So you have E here and B. These are adjustable parameters. They cannot be deduced from elementary kinetic data. Typically, the way they are deduced is from experiments, let's say, for burning velocities or ignition or for extinction of diffusion flames and so on. Okay, so the one-step model has been used here in description of flame stability and so on, where a strong temperature sensitivity shows up and thin flames show up. Here we will derive an explicit expression for the burning velocity, and then for using one-step global reaction. And then later on, we look at detailed kinetics, and then from detailed kinetics also we will derive an expression for burning velocity, and then in lecture 7, and then we'll compare the two to each other and see, or try to interpret the result we get from one-step chemistry in terms of the multi-step kinetics. Okay, so this is the configuration we're looking at. We looked at this earlier. You have one reaction here. You have fuel and air. At least one of these will be entirely depleted in the flame. For lean flames, all the fuel will be consumed. For rich flames, all the oxygen will be consumed. And for stoichiometric flames, both of these will be consumed. And so there's a condition here that YF burns times YO2 burns is 0 in the burned gases. Yeah.
So the diagram we have an absolute water of a state of the reaction. So probably going to get to it.
Yeah. So well, that's what it is. The preheat zone is order 1, let's say, and the reaction zone is much thinner compared to that. But we'll see that later on. We'll see that especially in the. You'll see. We'll skip some details here. You'll see that especially when we talk about multi-step kinetics. Okay, so problem formulation. Of course, combustion leads to an increase in temperature, and therefore to an increase also in the reaction rate. In the analysis, we assume very large activation energy, which means that also the sensitivity to temperature is very strong, which means when you go away from the maximum temperature, then the reaction rate becomes small very quickly. So that assumption is crucial here. We write the diffusion flux here in a very simple way, where the diffusion coefficient should be that of nitrogen, and we assume that the Lewis numbers are unities. Then these are the equations. This is the mass fraction, species mass fraction equation that we can write now here for fuel and for oxygen. You see both have here the reaction rate, and you now know immediately what we will do with these reaction rates and with these equations. We will use coupling functions to eliminate one or two of these. Next slide is the temperature equation. That's very similar to what we had earlier. And this here again is just a simplified form for the one-dimensional unstretched configuration. So we have 3 equations. The reaction source term depends on temperature, fuel, and oxygen. And so we have 3 unknown and 3 equations. And we can essentially solve that, but also what we can do here again is to use coupling functions to eliminate 2 out of these 3. And so by combining temperature and fuel equation, you can actually derive a coupling function here for the fuel that relates the fuel to the temperature, and you can derive a coupling function for oxygen, which also relates oxygen to the temperature. And now you can see if I introduce these expressions in the source term, then the whole equation is just a function of the temperature, and I've eliminated the fuel and the oxygen. So in the low Mach, this is very similar to what we had earlier. Low Mach number limit, pressure is constant. There are a few other assumptions that we'll make relating here to the density, thermal conductivity, and so on. We use thermal equation of state. And then here, of course, the reaction rate, as I said, is just a function of temperature. Right. So then, this is the only remaining equation. And in order to analyze this equation now, there are 2 assumptions that are being made. And these are given here. Because we assume that the activation energy is very, very large, you can imagine that you have a certain temperature where let me go back to this picture here, that you have a certain temperature, let's say this temperature here, where the reaction source term is very large. But now, the reaction source term has an exponential temperature dependence, which means if I go here further into the preheat region, let's say, and I go to a slightly lower temperature, because the activation energy is, let's say, infinitely large, that means that the reaction source term is exponentially smaller, and so essentially zero. Okay? No question anymore? Okay, so we define an ignition temperature where we say above this ignition temperature, you know, the source term is finite, and below this temperature, it shuts off to zero. So where were we? Here. So so we define a temperature Ti. Below this temperature, there's no reaction, omega 0, and we call this the preheat zone. And then in the reaction zone, this is for T larger than Ti. You know, you have chemical reactions, and there we assume, and then I said this earlier, we assume there that in this reaction zone, it's just diffusion and chemistry are important, and convection is not important. And again, you can analyze the equations, and that's an assumption that's actually very, very good. Okay? So these are the two assumptions that we make. And now we can actually look at the solution. So in these two regions. So we first look at the preheat region, temperature smaller than Ti. This means the chemical source term is zero. Going back to this equation, you see now you just have a convection diffusion equation, and you can, you know, the boundary conditions here are you go to minus infinity, gradient is zero, and the temperature is equal to the unburned temperature. And then you can integrate this equation because, look at this, rho u times SL, that's a constant, okay? And this is zero, which means, you know, you can just integrate this once in x, okay? And if you do that, that gives you, and you use these boundary conditions here, that gives you an expression here for dt dx. You see, go back to this. If you integrate this once, and here you just get the temperature, and here you have dt dx remaining. Okay, can solve this for dt dx, gives me this. Now this is interesting because you see the TDX is now a function of Sz. Okay, so if I knew the dt dx at a given temperature, I could compute Sz. Okay, but we don't. Okay, so now in order to you know, determine this missing quantity, now we look at the reaction zone. So now we look at T larger Ti, and if you look at T larger Ti, we assume that convection term is zero, and then you just have the diffusion chemical source term balance. Okay? And so that can also be integrated once if we now replace the spatial coordinate by the temperature. And so the dt dx here, we write this as dt dx, the d by dx, we write it as dt dx d by dt. And that's a good assumption because, or that's not a good, that's a valid transformation because the temperature only depends on x. So this here remains. But so if we do that, you see you can actually bring this dt dx inside of this derivative, and you get something like Cp over lambda times d by dt of dt dx squared. Okay? So here what we do is we just multiply this by lambda over Cp, and then you have the lambda over Cp times d by dx, and you can bring this inside and you get 1/2 this term squared. Okay? So if you have that, then you see you can integrate in temperature now. So this is the equation that you get. And these are the boundary conditions. Boundary condition here, the TDX at infinity is zero, gradient has to vanish, and the temperature has to be the adiabatic flame temperature, let's say. And then this can be integrated once in temperature, and then here you get the temperature integral of the source term, but then you get a relation here for dt dx. Okay, so that's the leading order solution in the reaction in the what do you call this? The reaction zone. And then on the previous slide here, we had the leading order solution in the preheat zone. Now, what's interesting now is that there is a point. So both give you an expression for dTdx, but there must be a point where both of these are equal. Okay, where the dTdx from the reaction zone is equal to the dTdx of the preheat zone. Okay, and so that's the so by considering this, you can actually eliminate the dTdx. Okay, and that's the so-called in asymptotics. It's called the matching. Okay, now you match the different zones to each other. So that's what we do on the next slide then. So we have this here for the preheat zone. We have this here for the reaction zone. And then there is a point where these must be equal. Let's say at Ti. Okay? And then you can equate these and you get a relation like this. And you see this here now gives you an expression for Sn, essentially. Now, this, of course, you see it still has the has this temperature integral here. It also has this Ti is still in the equation, and we don't like that because we haven't really specified what Ti is. So in order to look at this temperature integral, we have to look at the source term again. And the source term has two complications if you want to integrate this analytically. Number one, it depends on YF and YO2, which we don't know, but we said earlier we just replace these with a coupling function. Okay? Number two, there is a complex dependence here on temperature. And we want to get rid of this. And so we expand the temp. We know that this is important in the reaction zone. We know in the reaction zone the temperature is actually close to the adiabatic flame temperature, because if you decrease the temperature a little more, then the reactions shut off because of high activation energy. And so we expand this in a Taylor series, this term, just this term, in a Taylor series around Tb. Okay, that's what this is. And then we get a linear, instead of the 1 over T here, we get a linear relationship with temperature. Then I think there are some details now of the, the actual procedure, which I want to skip here really, or go very quickly. We introduce a non-dimensional temperature here, which essentially is the difference of the temperature from adiabatic conditions. So that here is a very small number. T minus Tb is a small number. So for this to be of order unity, you have this E over R Tb squared. That has to be a very large number then. Okay? Or the opposite, if we assume that E is very large, then you have this non-dimensional activation energy here, E over R, and that means T minus Tb over Tb, that needs to be now a very, very small quantity. Okay? Yeah, so this needs to be large. Okay? So then a few assumptions here. We assume that the density is the adiabatic density, or is the burnt density. Lambda is evaluated at burnt conditions and so on. And then you have these equations. Well, these equations, we don't need these anymore. We can introduce the coupling function. So now, because we did this Taylor expansion here, you see this is just a non-dimensional temperature theta. And so you see we split this up into two exponential terms. One is the exponential term at Tb, and the other one is here the actual temperature. And then you have the fuel and oxygen here. And replacing these with the coupling functions gives you this, term here that depends on temperature squared, essentially. Okay? So this doesn't look too easy, but it's not too complex either. And so this can now be put in the equation we had earlier, or the, we can evaluate the integration here, and you get this. And now, so we said earlier, we have an expression, it still has the temperature integral. We have evaluated, and you get whatever this is, okay? But then the second problem was we still have the TI, and we didn't really say what TI is, okay? So that's the last remaining problem, and for that we make an asymptotic assumption here again for large activation energy, and that is, if you look at this temperature integral, we know that the source term will become very small for temperatures lower than Ti, okay? Which means I might as well integrate this from Tu to Tb, okay? Rather than from Ti, because the integral between T unburned and Ti is 0 anyways, because omega is 0 for these conditions, okay? Why is that? Because we have assumed large activation energy. So that's not general, it's just under this assumption, okay? So we replace the Ti actually with Tu, okay? Okay, and then if you do that here, on this side, we're saying, well, because of the large activation energy, the ignition temperature is actually pretty close to Tb, okay? So there's not a big difference between Tb minus Tu and Ti minus Tu, okay? Because Tb minus Ti, that's again a very small number, okay? So we replace, in this expression, we replace the Ti with Tb. And then you see, if I do that, I have an expression here that only depends on quantities I know. And you see SL is then equal to all of this, and you see what appears here is, for example, the frequency factor of the reaction rate. This is what so I said earlier here, I said there's a chemical time scale. What is the chemical time scale? What puts a time scale in the reaction rate is the frequency factor. Okay? Is this B. And you see here you get some sort of a square root dependence on this B. Okay? Then you have here the adiabatic flame temperature. You have Tb minus Tu. And then you have this exponential term here again, which depends on E. And you have this S factor. And the S factor has three parts. It has a part that depends on O2 in the burnt, a part that depends on fuel in the burnt, and it has a part that depends on the temperature. Okay? So what you see from this is that this expression actually is valid for lean, rich, or stoichiometric. For stoichiometric, both of these will be 0, and the S factor here just depends on the temperature and the heat release. If you're considering a lean flame, then lean flame, all the fuel will be consumed, and there's no fuel left in the burnt. So this will be 0, and the solution will depend here on the excess O2, and for rich flames, it's the opposite. Okay, so this is what's shown here. So the equivalence ratio dependence here is considered by these three different cases here, where one of the terms, might remain, or for stoichiometric, none of the terms of the reactants remains. Okay, so so why is this? why is this interesting? First of all, you could say, if you ever wanted to know what is the overall activation energy, you can actually get that from this expression. Okay? I said earlier, overall activation energies are determined from experiments, from burning velocity experiments, maybe. But how do you get it if you have the burning velocity? How do you get from this the overall activation energy? Well, you can use a relation like this. And then if you have this measured and you know all the other things, then you can determine E here from this relation. Okay? Secondly, of course, once you know this, you have an expression. Once you know these parameters, you have an expression that allows you to compute this. But what's even more important is that an expression like this, it shows you how different parameters, even though it might not be right, okay, a lot of assumptions were made, it shows you how certain parameters affect the burning velocity. Okay? And again, we'll compare that later on with the result from multi-step chemical kinetics. So this just summarizes the assumptions again. I don't think we need to go through this again. We made a lot of little assumptions on the way. One big assumption was that of large activation energy, which led us to make all these assumptions here about temperature and so on. Okay, and I mentioned this earlier. Originally, this was done for first order chemical reactions where you either have excess fuel or excess oxidizer, but the expression that was shown here is also valid for very lean and very rich mixtures. And we see that for very lean and very rich mixtures, this reverts back to the first order reaction rate. It's like we had assumed that the reaction rate does not depend on the oxygen concentration at all. Okay? And for stoichiometric, you see the reaction rate is second order. Okay, good. So that was the analysis. Any questions about it? So we want to use this analysis now briefly to introduce some time and length scales for premixed flames. And then we want to move on to the multi-step chemical kinetics analysis. Any questions about this? Okay, good. So I want to do this quickly also. You see that you have a scaling relation now also. See, when I said earlier here, the flame thickness, it must scale with these quantities. Then you could say, well, most likely the burning velocity. What is the burning velocity? Burning velocity is the interaction of chemistry and transport. The transport is diffusive, d. The chemistry, has a time scale, t. And so probably also SL. There's a scaling relationship like this for SL. So SL is a velocity, is meters squared per second, and so d divided by Tc, that gives you meters squared per second square, and the square root of this then would give you just a scaling relationship for the burning velocity. Okay? Now, let's look at this. Is this right or wrong? You see that B here, B has units 1/2. And so if this is the inverse of a chemical time scale, then you see that the square root dependence of 1/t, that's correctly captured here. Then D, or rho D, with the unity Lewis numbers, is equal to lambda/Cp. Lambda/Cp here appears in the numerator, and you see, so this is also captured. So what this shows us is that the rigorous mathematical analysis, actually, it gives us the result of, that we get, just from, thinking hard about what the physical processes are. Or maybe, historically it has developed differently. Maybe They first got this expression, then they thought, well, what does it mean? It really means, something like this. Oh, so this is written here also. Okay, very good. So, good. So rho d is equal to lambda over Cp. I mentioned this. Now we can look at this actually as if we say this is the scaling, then we could go back and say, well, let rho d be let lambda over Cp, lambda over rho Cp, let that be this diffusivity, lambda over Cp, and then add a rho here. That's the diffusivity. Then all the rest must be the chemical time scale. Okay? So this means, this here is nothing else than this whole thing here divided by lambda over rho Cp. Okay, that must then be the chemical time scale to get this expression. Okay, so this is now, what I said earlier, chemical time scale that's the same as B. Okay, that wasn't exactly right. A rigorous definition that comes out of the asymptotic analysis of the chemical time scale is actually this. Okay, and you see here that the dimensionless activation energy again appears, or the square of that, which is then defined as here the Zeldovich number, and so that is that appears here in squared form. Okay, so since the Zeldovich number is something you can evaluate for different fuels. Typically, it's on the order of 10. The assumption that the non-dimensional activation energy is large is actually well justified. You see that this factor is then a factor of 100 actually in the burning velocity. So that makes then for a very strong influence of that quantity. And interesting also is that this time t is not just dependent on chemistry. The time t actually depends on E, and E in a one-step global reaction, I mentioned this earlier, it actually has to incorporate all the effects that were neglected otherwise. So it incorporates also effects of transport and how large or small the concentrations are and the gradients are in the reaction zone. And so if we define here a flame thickness like this, flame thickness is so what's interesting about all these scaling arguments is this. What characterizes a flame is its propagation speed SL, its thickness SL, and then you could also say a flame time, whatever that is. We have a chemical time scale. You could also say a flame time. Okay, and what are the independent parameters that determine these? Are just Tc and D. Okay, and that's it. And so, given this, you have only meter and second as independent units. You can jumble these. You can express one in terms of the other the way you like. And so the flame thickness then has to be has to scale here with the diffusivity and SL. And the diffusivity here again can be written as lambda over Cp. And then there's a flame time, and that flame time that has to be Lf, the flame thickness over SL. But then if we use the definitions we introduced earlier and plug this back in here, we see that actually the flame time defined like this. So this is kind of a macroscopic flame time. How long does it take for the flame you know, to burn over the laminar burning velocity, over the laminar flame thickness. Okay, that's what this time is. And you see that's the same as the chemical time scale. And that should just show you that that chemical time scale, as it appears here, that's a time scale. It's not just depends on chemistry, but you see that this is actually a more of a macroscopic flame time scale that actually says something about the you know, the flame as in its entirety. Okay, so what is a flame thickness then? And this is just a method for how you can define the flame thickness, or how, I mean, it's very obvious how we define the flame propagation speed as L. You can also, you know, have a quantitative definition of the flame thickness. Take the let's say you measure the temperature profile. You take the point of the largest slope, and then you take that slope and extend it here to burnt conditions and unburnt conditions in a linear line, and then where it hits unburnt and burnt, that defines the flame thickness. So that is a definition that you can use actually. That's a definition, first of all, that relates this just to the gradient at a given point, and it's also a definition that that can be, you know, determined experimentally. So if we use this, so this here was the expression we had for the preheat region, and if we take here the left-hand side, if we replace this here by this gradient, which is then TB minus TU divided by LF, then from this you can get an expression here for LF, which again comes out to be what we said earlier. Okay, so you see, I introduced these expressions like this just by scaling arguments. I said it has to scale like this. But you can also derive these rigorously from the asymptotic field. Okay. I think we can skip this here. The one thing that is mentioned here, though, is that the flame thickness here is actually also a measure for the quenching distance of a flame. So if a flame approaches a wall, then at some point it will quench because it is you have heat losses to a wall and so on, and that quenching distance, that is actually proportional to the laminar flame thickness, or it scales with the laminar flame thickness, as typically 5 or 6 times the flame thickness, but you know, depending on the wall, the temperature and all that could be different. The point is that it scales with this also, and again, this shows you that, you know, quenching distance, that's a length, and if that wants to influence the flame, then it has to be comparable with the scale of the flame, which is the flame thickness. Okay, so I think that that was it with this part. Any questions about this? Yes?
How do methane high flames?
Pardon?
How do methane and high flame thicknesses compare?
Hydrogen, so if you just look at this, yeah, so if you just look at this, you see, or let me see if we can write a scaling here that uses LF and SL. So LF is equal to, let's say, SL times TC. And if you assume that TC is roughly equal, then this would give you a much larger flame thickness. I don't think it's equal, though. The chemistry is faster, and so we can't see much from this. I think they're smaller, actually. The flame thickness is smaller, and that is because you burn so fast.
The hydrogen is smaller?
Yeah. I'm not sure, though. You know, if you look at the same conditions, but we can find out. I'll tell you tomorrow.
Okay.
Okay, other questions? Okay, so then the next section then. Oh, no, I said I want to show you this flame here. Make sure you don't fall asleep. So, this is a premix flame, and it has these holes here. So you have the fuel comes from here. You have these holes, and you suck in air here through these holes, and it mixes in this mixing region here, and then it comes out. Okay, why does the flame look so funny? Why doesn't it look like a jet flame? Because this nozzle is a little complicated. Why is the nozzle complicated? If I do this, I can't ignite this. Why can't I ignite this? Because the velocity is much too high. I just blow it off. So what you do in a technical device, if you want a flame to stabilize, now this here is because the flow velocity is much, much higher than the laminar burning velocity. Okay, so it can stabilize. Okay. Now, what if I do a diffusion flame? Diffusion flame is mixing control. Let's see. Diffusion flame would be I close all these holes here. See if I can do this. I think the spark now just goes in the very rich parts. It doesn't have air, and maybe that's the reason why I don't like that. Was that? Oh, that's right. I have this thing here also. Now I can't operate this. We'll do this later on. But we're talking about previous combustion now. So if you look at this nozzle, it actually has swirl vanes. So what you do in this nozzle, you create swirl in the flow. And if I put this back on, you actually see this. You actually see that the other flame kind of looks a little bit like this. And because you have swirl, the streamlines diverge, you get a recirculation, and that recirculation brings back hot burnt gases, and it creates long resonance time, and this is why this burns. And you kind of see the diverging here, and you know, the recirculation then leads to a recirculation zone. So now what happens if I close these holes, which means then I've only fuel come out. Okay? So let's do that. I lock this, and now take the premixing out, and this is my diffusion flame. Okay? So you have now only fuel come out, and you see, so this is a cigarette lighter on steroids now. You see, is the exact same thing we had yesterday, or let's say similar thing we had yesterday. You see the blue thin reaction zone very close to the nozzle, and then you see the flame downstream. It's swirling a little bit, which is why it looks a little funny, but then you see the soot forming and so on, and because now it's a lot larger, you see it doesn't get really turbulent, but it gets, you know, unstable. And then what you see is sometimes you see the smoke coming out, especially when I decrease the residence time, okay, if I decrease the flow or the mixing time scale by, you know, shaking it a little bit, then you see it doesn't have enough time to oxidize the smoke or the soot, and then you see smoke coming off on the top. I'm not sure if you see this. I did this once in class. I'm not sure if that was the year you took the. I have a burner like this in my lab, and but the swirl nozzle, it's just stuck on. It's not screwed, and so I was doing this. I was going like this, and the thing flies off in the window. The window didn't break. I was lucky, and I didn't hurt any of the students. They were more lucky. Okay, so what I want to show you though is I was talking earlier about very intense combustion. This is the diffusion flame, okay? And that premix flame I was showing you, that has the exact same heat release rate. If we assume the fuel burns all, you know, then it has the same fuel flow rate, so it must have the same heat release rate. But look at how different it is. This is the diffusion flame, and this is the premix flame, okay? So the premix flame gives you a much more intense burning rate. I would pass this around. I'm a little uneasy with it, though. So you guys can come later and look at it. Yeah. So soot is an unburned part of the fuel, but the soot volume fraction is so small that doesn't matter too much. And also, if you look at it again, as long as I don't have the soot coming out of the top, the soot is all burned out also. Okay. So you can do that at home if you have a candle, for example. You see the smoke also. Hopefully, it all burns out. But sometimes, when you straighten the wick, then you get a lot of fuel, and then it smokes. And then, if you turn it around, you decrease the fuel flow rate, and it stops. But also, if it's not sooting, you can now try to. So the only reason why it doesn't smoke is because all the soot gets oxidized in the reaction zone. So you can try to prevent that. You can do that by just sticking a spoon or a fork in the flame, because that will cool the flame so quickly that then it doesn't oxidize anymore. So you just stick this thing in and it will smoke. You had a question, yeah?
Why is the sound generally so different?
That is because of it's not the flow rate. The flow rate is roughly the same, except, you do have a higher flow rate. But the point really is the unsteady heat release. You have very strong heat release confined to a very small region, and that will just send out pressure waves, which you hear.
So it's the
It's intense
intense combustion.
combustion, unsteady combustion.
So why is it longer than the length of mix?
Yeah, because it's mixing controlled, and mixing is slow. And this thing, it will be as long as we look later on, we look at flame length of diffusion flames. It will just, until it's all mixed out. And because, in this case also, that is because the flow rate now is lower. It's not turbulent anymore. And because of that, mixing also is very slow. So if I make this turbulent, I probably can't make this real turbulent. But you see, it gets smaller, actually, if I mix faster. Yeah. This is why, in an aircraft engine, you want to have we'll talk about this later on, turbulent combustion. You want to have turbulent combustion. If you have laminar combustion in an aircraft engine, guess how much larger the engine would be. Who wants to guess?
20 times.
10 times. It's 100 times. Okay, that's just a rough estimate. Because you can show that the rate of mixing, of molecular and turbulent mixing, is proportional to the Reynolds number. Okay? And below a Reynolds number of 100 is not turbulent. Okay? So if you're turbulent, then the rate is at least 100 times faster. So laminar combustion, the engine would be, 200 meters long. It wouldn't fly. Okay? The only reason why an aircraft flies is because of turbulent combustion. Okay, so let's move on. So we wanted to not talk about chemistry. However, we're talking about combustion, so there must be some chemistry. And what we want to do now, in the previous lecture, we talked about the asymptotic analysis using one-step chemical reaction. But however, we said there are issues with making that assumption, and we'll see later on what these issues are. And so now we want to talk about an analysis that's based on real chemical kinetics. And right, this is basically what this says. So let's see if there's a reference here. There's no reference here. There has been a very famous paper by Williams and Peters on the asymptotic structure of methane flame, and we will look at this now. There are other analyses here by Seshadri, there are analyses for other hydrocarbon flames. For example, here for, well, not here, but for other fuels. And, but what we see is that these are typically very similar. What is different is if you do the analysis for lean flames, stoichiometric or rich flames, there are actually 4 different regimes for methane flames. Lean flames, stoichiometric, slightly rich, and very rich. Where the stoichiometric and lean is the same. So let's say there are 3 different regimes where the analysis has to be different. And here we'll just look at the lean flames. We will look at the, we'll start out with a reduced chemical mechanism, and that's the so-called 4-step chemical mechanism. And the 4-step chemical mechanism is very interesting because it has basically all the information that is necessary to describe, for physically correct reasons, what happens in the flame. Okay? What is most important in chemistry, I said this earlier, is always the radical balance. You have a reaction that produces radical, that starts out with 1 radical, makes 2. That will tremendously accelerate the combustion process. Why? Because you make 2 out of 1, and then the next step you make 4 out of 2, and then, so this is an exponential growth. If you have a reaction that consumes radical, you get an exponential decay. Okay? So most reactions, most chemical reactions, actually, they don't produce or consume radicals. They're radical neutral. Okay? But some consume or produce radicals. And these are the most important reactions in combustion. Okay? Now, the 4-step mechanism is based on a full, chemical scheme, and it starts with a systematic reduction, systematically eliminating all the reactions that are not important. It's important to note that the 4-step mechanism is not intended to produce the exact right results. Okay? If you use that, actually, you will get differences. You don't get the same burning velocity as what you get with the measured, with the full mechanism. Okay? It's intended to just reveal the physics that you have in the flame. Okay? So it starts out with eliminating all the reactions that are not important, and then introducing so-called steady-state assumptions. Now here we don't have much time enough to talk about what steady-state assumptions are, but you can think of it as this. If you have a mass fraction equation, it kind of looks like this. You have d rho y dt plus del dot rho u y minus d by dy, or minus del dot rho d del y minus m dot I is equal to 0. That's a specious transport equation. Now, when we make a steady-state assumption, we assume that a species is produced fast and it's consumed even faster. Okay? So this means I split up this term into a production and consumption term, and I have a difference here of production and consumption. And because each one of these two, then, production and consumption, is very, very large, let's say, that means each one of these is much larger than each one of these terms. Okay? Which means I can neglect all these terms compared to these production and consumption terms. And what this means then is that, you see, if I have an expression m dot is equal to 0, that has no differential anymore, so that gives me an analytic expression for the concentration of that steady state species. Okay? So that's, in just 2 words, that's the meaning of steady state assumptions. If you do that, you always reduce, you get analytic expressions, and you reduce the number of differential equations that describe the problem. So we assume here the stable components are methane, O2, H2O, CO2, H2, and CO. and all the others are in steady state, except we keep one radical in non-steady state because we want to use this to describe the effect of radicals on the burning velocity. So this represents the effect of radicals in general, but also this radical is very important in the competition between so-called chain branching and chain breaking reactions. Chain branching reactions, relating back to what I said earlier, chain branching reactions are reactions that produce new radicals. Chain breaking reactions are reactions that consume radicals. Okay? And there are two of these reactions which are most important. And, in this particular chemical scheme, these are called reaction 1 and reaction 5. And they're given by these two reactions here. And you see that the H radical is important in both of these. Now, I want to step back and tell you something about these reactions that is not in your notes, but you will immediately see that it makes sense. And that is the following. So these two this reaction here, that it turns out, does that consume or produce radicals? It produces radicals. It takes one radical on the left, and it makes, let's say, two radicals here on the right. Actually, you always have to count the O radical twice. That counts as two radicals, really. And so you could say on the right hand side of three radicals, you have one. So this executes once, makes two radicals. This reaction here, does this produce or consume radicals, or is it neutral? It looks like it's neutral because you have an H on the left, HO2 on the right. HO2 actually also is a radical. Turns out, though, that HO2 under combustion conditions, it actually under combustion conditions, actually the HO2 it recombines with itself to form hydrogen and oxygen. So it doesn't act as a radical. Okay. So what that means then, you have a radical on the left, no radical on the right, and so this reaction 5 is actually radical consuming. Okay? So these two are the most important radical producing and consuming reactions. That's fact number one. Fact number two is, and I said this earlier, the most important thing in combustion is the radical balance. So combining these two statements, these are the two most important reactions for combustion of hydrocarbon fuels and also of hydrogen, of course. So it's worth to spend a minute to look at these reactions and see which one is more important. If the first one's more important, you get chain branching and you get an explosion, whatever. If the second one is more important, then radicals go away and the flame will extinguish. Okay? Which one is more important? Say it again? The right answer, the correct answer is it depends, of course. And it depends on the temperature. They both have a temperature dependence, but they have a different temperature dependence, so one might be more important than the other in certain regimes. So it's interesting, then, to look at the ratio of the two reaction rates. Okay? So I have a reaction rate, omega 1, which is equal to K1 times the concentration of H times the concentration of O2. Okay? K, of course, not sure if we introduced that, but K is equal to B times T to the nth power times exponential of minus E over RT. Okay, so that's just basically the the rate coefficient or the Arrhenius coefficient. Okay, omega 5 is equal to K5 times CH times CO2. And then you see it has a third body also. This goes with a third body, an inert body. What this means is that here you have H and O2. They come together. They form an activated complex. And really what they want to do, because they have a lot of this energy left, they want to break up again. Okay, so that means nothing happens. But however, if when H and O2 come together before it breaks apart, there is an inert component, let's say nitrogen, or let's say nitrogen. It comes and collides again with this activated complex. It takes up some of the energy. Then the HO2 can stabilize. Okay, the nitrogen that can handle the excess energy, it will not break apart. It will just stay inert. Okay, so this depends then on the concentration of H, concentration of O2, and the concentration of that third body. Now, what's interesting is we said if this is faster, then we'll have, it will burn. If this is faster, it will extinguish. So what we can do now is we can look at the ratio of the two. Omega 1 over omega 5. If this ratio is larger than 1, it will burn. If it's smaller than 1, it will extinguish. Okay? So, and that is the nice thing here. Now we get K1 times CH times CO2 divided by K5 times CH times CO2 times Cm. And you see CH and CO2, they go away. And all that's left here is K1 over K5 times Cm. Which means, so Cm, that's just a concentration of, whatever could bump into this and take up the excess energy. You could say that's the total concentration. The total concentration is equal to P over RT. Okay, so I continue this here. I could say that is equal then to K1 over K5 times P over RT. So you see that this is the question, is this larger or smaller than 1? That depends on pressure and temperature. Because K1 is only a function of temperature, K5 is only a function of temperature, and then here we have another temperature, and here we have pressure. So if we say we want to look at a case at 1 bar, okay, or atmospheric pressure, pressure is fixed, and we can determine the temperature where the ratio is exactly 1. Okay? And we call that the critical temperature, or we call that the so-called inner layer temperature. Okay? So I want to say when this here is equal to 1, when this is equal to 1, that gives me the so-called inner layer temperature T0. If the temperature is larger than this, so let me just show you, show you how this looks like. So if I plot K1 and K5 as function of, 1 over the temperature, then K1 has a certain activation energy, so it kind of looks like this. And K5 has almost 0 activation energy. It has a very small coefficient here. Let's forget about the coefficient, and it will look like this, roughly. Okay? So there's a point here where, so this is fixed for a certain pressure now. And then you see here, so this is K5, and this is K1. Okay? So at very high temperature, K1 is faster, which means you produce radical, it will burn. When you go below this inner layer temperature, then you see K5 becomes faster, and so this will consume radicals and it will extinguish. Okay? Now, when we earlier we said, well, let's define a Ti, and we say the activation energy is large, and below the Ti there's no chemistry, and above Ti there is chemistry. Of course, there's no shutoff point, because in that one-step model, the reaction rate was just exponentially. It will just get exponentially smaller. Okay? But here you see, in real kinetics, there's a real shutoff point. If you go below that temperature, then the reaction will cease. Okay? Because all the radicals will be taken out. Okay? So that's the relevance of these two reactions. The competition of these two reactions, I said this earlier, here causes this very strong nonlinearity. And this competition of these two defines a temperature, which we call the inner layer temperature. That's very important. Okay, so these reactions are important. They lead, with the steady state assumptions here for OH and O, which which appear here, leads to the global reactions 3 and 4 of the 4-step mechanism. So you can look at this. This is how we derive these global reactions. This here is starts from the reaction H plus O2 goes to OH plus O. And the way you derive the global reactions, you say there's one reaction that's slow. That's the rate determining reaction. And all other reactions, that are fast, let's say, or other subsequent reactions are fast. So this means that once I execute this first reaction here, this is a slow reaction. If I execute this once, this OH or this O will be instantaneously converted into OH and H. And this OH, or both of these OHs, will be instantaneously converted to H2O and H, which means we can just add these up, and the result here will be O2 plus 3H2 goes to 2H2O plus 2H. Okay? That is based on this reaction. And it shows you what I said earlier. It shows you that once you execute this, you actually produce two radicals. Okay? I said earlier for that, you have to know that O counts as two radicals, really. And you see this here. O plus H2 is two radicals here on the right-hand side. And this is a fast reaction, goes back and forth very quickly, which means that these are equivalent. Okay? So this is reaction number 3. Reaction number 4 starts then from this reaction 5 that we discussed earlier, H plus O2 plus M. Goes to HO2 plus M, and here you see what happens to the HO2. HO2 plus H goes to H2 plus O2. The other reactions that have the same effect, but the net effect here is if I add these two up, you see H plus M goes to H2 plus M. This consumes, net effect, it consumes two radicals. Okay? And which is what we said earlier. How do you know these things? How do you know that HO2 under these flame conditions, under different conditions, for example, when you talk about ignition in certain temperature ranges, something totally differently happens with the HO2. Okay, but the question: how do you know that this is the main consumption reaction for HO2 in flames? Well, this just comes from doing numerical simulations and then looking at the results. Okay? You can see what is the main reaction that consumed HO2 under these conditions. That's this, and then you can stick it into the analysis. Okay? So these are two of the 4 reactions. Then methane here is a little longer chain. Methane is mostly consumed, so that's the fuel now. It's consumed here with H, leading to methyl plus H2. And I said earlier that methyl plus methyl can go into the C2 chain, and that's relatively fast. Here we have, if it stays in the C1 chain, which is the main consumption path, then the methyl radical is very stable. It's not like an H radical. It's a very stable radical. And because of that, it needs a lot of power to, to destroy this. And so the O radical, I said this earlier, counts as 2. This is a very powerful radical, which is why the methyl radical is mostly consumed here with the O radical. So CH3 plus O goes to the formaldehyde plus H. And now let's count radicals again. How many radicals on the left side?
2.
How many? 2. Is that right? Who thinks it's more than? Yes? 3. Very good. Because I said the O cuts twice, right? So you have 3 radicals on the right, 1 radical on the left, 1 radical on the right, so this consumes 2 radicals. Formaldehyde then goes to the CHO, CHO goes to CO plus H, and then you know, we want to get rid of here the OH, the O and the OHs, which is what this does. And if we add this all up, we get CH4 plus 2H plus H2O plus CO plus 4H2. So what does this reaction tell us? It tells us you convert once the hydrogen radical here attacks the methane, it will be converted very quickly to CO and H2, the stable intermediates. Okay? And it will do, while it does that, it will consume 2 radicals. And so this is why methane is a relatively slow fuel, because the consumption of methane consumes 2 radicals. Okay? You have a question? Yes.
Can you explain why oxygen comes to?
Yeah. Right. I mean, you could look at it from a chemical perspective. It has 2 free valences, but then really I look at this more here like this. This is a reaction. So there's slow reactions and fast reactions. This is a slow reaction. Okay. Sorry. This is a slow reaction. So you can't say what's on the left is the same as on the right. When this is very slow, but if it happens once, you produce radicals. The other reactions are very, very fast. They go back and forth very quickly, and they equilibrate the different the amount you have of the different radicals. And one of these reactions is this reaction here. This goes back and forth very quickly, and from this you see, because it does this, you see that the O is equivalent to having an OH and an H. Okay, and that's why we say it actually counts as 2. And you see that also here. You know, we said here, you know, this is 1 and this is 3, let's say. So you produce 2 radicals. That's what I said, if you count it twice. But if then you add it all up, you see the global reaction tells you that actually. You could have started from the global reaction and said, look, the global reaction, you know, produces 2 radicals, which means, if I go back to this, it really means that O or OH needs to count as 2. Okay? Was there another question? Yeah. Okay, so okay, so these are steps number. So here, this is where we were. This is the fuel consumption then, and then the fuel consumption produces CO, and then here we have a reaction that the main consumption reaction for CO is CO plus OH goes to CO2 plus H. Now if we eliminate the OH here again, we get CO plus H2O goes to CO2 plus H2. That is the so-called water gas shift reaction. And it just shows you how CO is converted into CO2. So these are the 4 reactions we have now in the 4-step mechanism, and they all have a specific meaning. The first one is the fuel consumption. The second one, the fuel consumption into stable intermediates. The second one is the consumption of stable intermediates into products. The third is the radical consumption, chain breaking reaction. And the fourth is the chain branching reaction or the radical formation reaction. Okay? So these actually, because we say always the first reaction is slow and all the others are fast, it means that this occurs once if the first reaction occurs once. Okay? And this means that the global reaction, they actually go with the reaction rate always of the reaction that starts the reaction sequence out. Okay, so you know, this 1 here goes with W11 here, which is the consumption of methane. The second one, the CO conversion goes with this rate. You know, the 3 here goes with the H plus O2 plus M rate, and this one goes with this rate.
How is this is a systematic reduction from a much higher?
Yeah.
So there are some articles which reference which produce global reaction which deal with only measurable species. How do those compare with each of these?
You mean you're talking about let's say empirically reduced?
Yeah, for example, the force mechanism that Westwood trial, which does not have any radical.
Yeah, yeah. So there are two differences. The first is if you have radicals or not. That makes a big difference because we see that the radicals. We see over there that the radicals introduce very interesting nonlinear behavior. That's number one. The second is if you have mechanisms that are empirically derived, then the rates are actually very different. Here, the rates are all based on the real measured chemical rates. And the only errors you get here is that, for example, I said earlier, you actually need to consider the C2 chain also. That is not considered here. Actually, if you do the reduction, doing this reduction, you can also consider all these secondary chains, which we didn't do here. But in a real systematic reduction, you would actually do that. You would come out with the same reactions here, but the rates here would be very complex. Okay? Okay, so you see that the reaction rates here, they still have OH here, for example, or the reverse of this here has O, and so we need to have expressions for these. You get these from the assuming equilibrium of these two reactions here, which is a good assumption because both of them go back and forth very quickly, and you see that introduces here the equilibrium constants. So if you plug that in then, you get all these reaction rates here where some of these reactions we consider forward and reverse, and the others we just consider forward reactions. Okay? And what's interesting about this now, this is a closed system, has eliminated everything you don't need anymore. It is based just on chemical kinetics, which you can look up in published literature here, for example, K1 and K5, and also on the equilibrium constants, which are just based on thermodynamics, which are given here. So this is a closed system which you can actually take, implement it in the code, and solve it. Now, what's interesting is we can also eliminate the radical here. Eliminate the radical does not necessarily mean eliminate the effect of the radical. We still have it there. We just assume it's steady state. Okay. If we do that, then you see you get a reaction system that now looks like this, and then you get a steady state relationship for the radical. And again, if you look back at this mechanism, it shows you this mechanism. It shows you reaction 1 consumes 2 radical, 2H. Reaction 3 consumes 2H, and this produces 2H. Okay? So if I set this now into steady, so if I have a transport equation, now L of H, this L here is supposed to be the operator here on the left-hand side, the transport operator. That's equal then to the chemical source terms, which is minus omega 1, minus omega 2, plus omega 4. Okay? And that we want to assume this to be steady state, so it's equal to 0, which gives us a relation here for the H radical, which is given here like this. And what's important, without going into details, what's important here is that the H radical now, depends here on the equilibrium concentration, times 1 minus K5 and K11. 5, that was the main chain breaking reaction, H plus O2 plus M, and 11 was the fuel consumption reaction. Okay? This is interesting because at temperatures of 1400 Kelvin and above, this second term here in the brackets is small, and we saw that here. It's become small, relatively small at high temperature. But this term here is very large. Okay? And it follows then, if this becomes large, if this ratio becomes large, it follows that CH4 has to go to 0, otherwise this doesn't have a real solution anymore. Okay? So in order for this to produce a real solution, the fuel has to go to 0 in the at these higher temperatures. And so then also what you see is that for low temperatures, this term here becomes large, and this means that H actually goes to 0 in the chemically or in the preheat zone, which is therefore chemically inert because there are no radicals in it. Okay. So the steady state. So it's not even the transport really. It's the transport of thermal energy into the preheat region and fuel and oxygen into the reaction zone, which then give you a steady state relation here for H, which basically tells you that in the preheat region you cannot have any H, and in the reaction zone you cannot have any fuel, or the fuel has to go to 0 very quickly. Okay, as soon as the fuel becomes an appreciable concentration, the H all is consumed very quickly, and you are in the preheat zone. Okay. You can reduce this further to a two-step mechanism. This two-step mechanism is in your notes again. I don't want to go through the details here, but then come here at the end maybe to the. Let me see how far this goes. Yeah. To the result of now you have this four-step mechanism, and you can do an asymptotic analysis similar to what we had earlier, but now with these 4 reactions or 3 reactions. And I don't want to show the details here, but I want to show you what the result is. The result, we saw this already, is that there is an inner layer temperature here, T0, and that T0 is given here by this the competition here between reaction 1 and 5. If you're below T0, this essentially the reaction is frozen. Then what we saw is that fuel basically is very, very small concentration in the reaction zone. It will be consumed in the reaction zone, and by diffusion it comes in. Diffusion, there's no chemistry, there's no radicals in the preheat zone, and because of that, there's no chemistry. And then there is a reaction zone where you convert the fuel into CO and H2. So you have the H2 here, and then there's an oxidation layer that comes subsequent to the reaction zone, and in this oxidation layer, H2 and CO are converted to CO2 and H2O. And so you see this here is of order epsilon. Epsilon is much smaller than the preheat zone. The thickness of this oxidation layer is much smaller than the preheat zone. This here is of order delta, is not mentioned here. And the delta then again is much smaller than epsilon. This comes out of the asymptotic analysis and the rate ratio, the rate ratios that define these thicknesses of these layers.
So of those, would you consider the flame length, flame thickness?
Yeah, that's interesting because we would say the flame thickness is the whole thing, okay, is all of these. However, if this here is order 1, and this is epsilon, and epsilon is much smaller than 1, we can forget the oxidation layer. And if delta here is even smaller than epsilon, we can also forget the delta. So you have to look at this. This is the preheat zone, and then at the end of the preheat zone you have a thin reaction zone, but it's much smaller than the preheat zone. So when you talk about the flame thickness, essentially it's the same as the preheat zone thickness. Okay. Okay, so this has now the details of the asymptotic analysis, which we are going to skip here. And again, it's in your notes, so if you want to look at this, feel free to do that. Yeah, so here's the delta, by the way, that I just mentioned. Let me just see how far I want to skip this now. To 644. Okay, so I just want to look at the result real quick. Yes, so result of this, so 6:44. We will actually work today until 12:20 because there were so long lines yesterday. We were asked to stagger a little bit. And so Professor Wang will finish a few minutes early, and Professor Lubin will go very long, and I negotiated that we go only 5 minutes over. Okay, so so that should actually, in theory, give you shorter lines at the buffet. Again, I will stay here actually. If you have questions or you want to talk about, some questions, I'm happy to talk to you. So the asymptotic analysis leads to this. This is the expression you get for the burning velocity, and you see it looks a little more complicated than what we had earlier. And it depends now on this inner layer temperature. And the inner layer temperature actually comes from this expression, which is now a function of the pressure. So the way this works is you fix the pressure, you say 1 bar. From that, you compute the inner layer temperature. You see inner layer temperature, 1 bar is roughly 1400 or 1350 Kelvin. And then with this T naught, then you can go into this formula, and then you get the burning velocity. And the burning velocity we get is 55 centimeter per second. We said earlier, for methane, actually it's more like 40. And so you see that this gives you a small difference, or it gives you an appreciable difference. However, we want to maintain that it's not to be quantitative, it is to reveal the physics. Well, again, I mean, this is what gives you T naught, and this is what gives you the actual burning velocity. What's interesting here is that there are only 3 rates, chemical rates that remain here, and this is the main fuel, the fuel consumption, the chain branching, and the chain breaking reaction. And there you have some more equilibrium constants, but the kinetics only comes from these 3 rates here. You see you get these temperature functions here. TB minus T naught, that is interesting, will be interesting later on, because TB minus T naught, that means if T naught, that's just a function of temperature and pressure. Fix the pressure, only function, I'm sorry, T naught is just function of pressure. You fix the pressure, T naught is given. Okay? TB is a function of equivalence ratio. Okay? Which means if you go leaner and leaner, TB goes down. And at some point, TB will be the same as T naught. You see you have a 0 here, and there's I need to go to 0. Okay? So we'll use that later on. That fact, we'll use that later on to determine flammability limits. Right, so I just mentioned this. If T naught reaches TB, then the burning velocity vanishes. And that's here, for example, at 20 atmospheres, this would happen, or this happens at about 20 atmospheres here for this case. Okay, so and you can of course you get different TB here by dilution or by just going lean or very rich. And as I said, we'll use that later on to explain flammability limits for different fuels. So then we can look at how does this this model compare. So this was an expression we had for the for the burning velocity. We can look at how does this compare with the result we got for the one-step global reaction. Okay, and in order to do this, we said we look at the limit of large activation energy. Then you can look at a differential here like this and compare these to each other from the different expressions. So if you compute this from the large activation energy relation, you get this. If you compute it for this here, then you see you get these 2 different terms here. What's interesting now is that, so now we can equate these with each other and see what this implies. Let's say here for the activation energy or whatever. One thing we see here immediately is that TB minus T naught, that is relatively small. TB minus TU, that's relatively large. Okay? So the first term here will be very large, the second will be very small. So, you know, for the sake of this argument, we can forget about the second term. Okay? Which means we can equate this here from the one-step model to this here from the multi-step chemistry. And so introducing then this relation here. This is a relation that came out of the asymptotic analysis. Epsilon times Z naught. Z naught here is basically the hydrogen mass fraction, and epsilon here is the thickness of this oxidation layer. If I introduce this here, and I introduce the Zeldovich number, then from equating these two, so this is this part here, is this now. So then from equating these two, I do this because then TB minus TU goes away, and I'm left with an expression here like this, which then essentially says that the Zeldovich number of the one-step model has to be 4 divided by epsilon Z naught of the multi-step model. If Z naught here, that's a scaled quantity. Epsilon here is a very small quantity, which shows that the assumption that the Zeldovich number is very large, it actually corresponds to the fact that this oxidation layer here is very small. Okay, and that's pretty much what this says here. So therefore, the oxidation layer in the hydrocarbon chemistry, that plays a similar role as the reaction zone in the one-step asymptotic field. Okay, so that's kind of what comes out of this comparison of the two different results. The one makes the assumption that this is very large. The second one makes some assumption of some finding. Epsilon, actually, that's a rate ratio. So that's something you can actually evaluate. And it turns out that is very small. So, but it relates the Zeldovich number with the oxidation layer of the multi-step. Okay, at the end here then, there is a section that makes use now of this result. I want to skip this, but the idea is this. This is what we got for methane. And what we see is it depends here on TB minus T naught to the 4th power and a few other things. So let's say you use that result, but you make this here a big coefficient and just keep the TB minus T naught to the 4th power. And so this here would then be a coefficient. And then you can use this as a fitting function, not just for methane, but also for other fuels. Okay? And so this here shows how a fitting function was developed for different fuels. It has a few coefficients here, but it relies on this general form of the burning velocity as function of these quantities. And once you know all these parameters, then you can go back in the equation and compute the T naught and use that in the second equation to compute the burning velocity for these fuels at different pressures, temperatures, and so on. So this is something you can use in a code if you just need the burning velocity and nothing else on the fuel. Okay? Yes?
Does it mean that mechanisms for the higher hypothesis as like similar to because when you're fitting functions,
yeah. So you're saying if that means that if you would do the asymptotic analysis, if you would get the same result or a similar result, yeah, that's basically what it means. For hydrogen is different but for hydrocarbons is kind of similar. And so what's interesting here about this is that if you want to fit a complex function, that's always very hard. But if you have a basis function like that, then fitting actually becomes much more accurate. And so this doesn't say it's exactly the same, just says, well, you know, it might be very similar, and so it's better than just doing a polynomial. Yeah. Other questions? No? So I'll let you go, enjoy your afternoon, and we'll start then tomorrow morning with the fusion flames. Okay, see you tomorrow then.